Anyway, let's get underway. So thank you for coming along. So last month, we talked about how astronomers, the main methods that astronomers use to detect these exoplanets, planets outside our solar system that go around a host star or maybe go rogue through the planet, through the galaxy. And we learnt how there was very close to 6,000 exoplanets they've now discovered, including entire solar systems like this one here. It's an artist's impression of Kepler 11, which was discovered by Kepler only within the first year of its operation, with 6 planets going around its host star. So from there, we next ask ourselves is, how many of these 6,000 odd exoplanets have the conditions to support life? We also ask ourselves how many of these conditions actually do support life, have life on them. And if we're going to be searching for Earth 2.0, we better know what we should be looking for. And that's the point. And so for that reason, tonight's talk is part 2, and it's called Origins, Conditions and Signatures of Life. What should we be looking for? And if there's one thing you take away today, my main message is this. Life in the galaxy will be abundant, it will be detectable, but it will be mostly simple slime. Not too far off some days on Earth. So, I've split it into these sort of main 4 chapters, if you will, and then we'll sum up. So we're going to talk about the origins of life. What is life? If we're going to be looking for it, we better know exactly what we are looking for. We've only placed Earth as the only place we know that, as far as we're aware of, where there is life as we define it. So let's study Earth, how life got going on Earth. Let's learn about everything we can about the history of life on Earth. That makes sense to give us a better understanding of what else there might be out there. We'll talk about what conditions does life require, so we know what conditions we should be, what sort of planets and so on that life is going to find most likely to be favourable. We're going to talk about the signatures. What should we be looking for in terms of telltale signs of life? And then we'll sum up and talk about the implications of what we've talked about. In particular, what can we expect? So let's start. Origins. What is life? How did it start? And how did it evolve on Earth? And that really is the point of that, is to answer the question, will there be extraterrestrial life? And how common will it be there out there? That is what we hope to answer by looking at life on Earth. Let's get some messages. It's only a sample of one, but it's all we got. Let's run with it. Okay, so there is no one perfect definition of life. There's all sorts of rules and exceptions and so on. You can run around chasing your tail. But there's 2 very important considerations that are important in trying to get your head around some sort of definition, of workable definition of life. First one is the most smallest or the most basic unit, the atom, if you will, of life is the cell. That's really, really important. All life must have come down to a living cell. Cells have 3 basic components. They're all different types, specialized cells and so on. They've got 3 basic things all in common. First of all, they're enclosed by a membrane. You might think, well, that's damn obvious, isn't it? But the importance of that, it provides a barrier to the outside environment, which allows to have a nice stable environment on the inside, but also to select and concentrate and bring in ingredients and fuels and so on that you need from the outside environment. Bring them in and concentrate them. So that is important. You've got the inner cytoplasm, and that provides a nice, stable interior condition for the important chemistry of life. Once again, you take that for granted, but there's a lot of complex chemistry that's got to go on, that's got to have the right conditions. The cytoplasm is able to provide that because of the membrane. And then you need DNA. As you're about to learn, that an important part of life is reproduction. You need DNA is necessary for storing and copying all the information that you need for reproduction, growth, and to survive, and so on. So that's a really important concept. All life needs a cell. That's the atom, if you will, of life. The second consideration is that the function of life, or the function of a cell, is to survive and to reproduce. That might seem obvious, but that's really important. You've got to survive and you've got to reproduce. So living cells must possess all these three properties, part of our working definition, if you will, of life, which we will explore. Metabolism, they've got to copy, self-replicate and grow, important self-replicate, and it's got to adapt and evolve. My little mnemonic for remembering that off the top of my cup is MCA. MCA records, I don't know, maybe I'm an oldie and things like that, I don't know if they even still exist. So metabolism, so what is metabolism? And essentially it's a set of chemical reactions, life-sustaining chemical reactions, and it involves extracting nutrients and fuel and food from the outside environment, bringing it in, running a series of cellular processes and so on, and converting what you can get from that nutrients and fuel, converting that into your building blocks of life that make up your cell. It's got to be the cell membrane, proteins, lipids, DNA, RNA, and so on. We're going to talk quite a bit all about them. And it's also elimination of waste. You forget that. That's all part of metabolism, that cells must be able to do that. Cells must be able to copy, self-replicate and grow, which means they must maintain and repair any damaged cells. Any damage comes to a cell, it's got to repair itself. It's got to be able to grow and to survive, but also it's got to make copies of itself. So it's got to be able to reproduce. And incidentally, I throw in here, this is going to be a common theme that you're going to hear time and time again in this talk. All life, as I've written here, uses DNA. There are so many universal things in biology that all of life, right across the board, uses. And the third one, it must adapt and evolve. And what this means, it's got a hereditary system, in other words, some sort of system of where information is passed on to offspring, whether it be offspring cells or offspring in terms of living beings. But also importantly, it's got to exhibit variability. In other words, it's important that it's able to stuff up occasionally, make an error in its copying process. Because the importance of that, it'll allow changes to occur, changes in structure, changes in function, which in turn, some of those changes are favourable, some of them aren't. And the ones that aren't die off, but the ones that are favourable tend to reproduce more. And if you've got changing environments going on, you're going to need change in structure, change in function. And that's what allows that to happen, to survive and reproduce in a changing environment. Our environment naturally changes. Nothing in this world is forever. Everything changes. And life has to, part of its definition, keep up with those changes. It's got to have a system in place whereby it can't help but make mistakes. Imperfections make us perfect. So that's our main considerations in terms of life. And there's another one too, that if we're in the context of we're going to be looking for life elsewhere, for our Earth 2.0, we've got to look deeper into life on Earth. And one of the things that you've noticed probably is that all life on Earth is carbon-based. All life, which means its big structures are all based around carbon. And a lot of people say, well, often you hear people say, well, why not silicon? Why can't it be silicon? Possible, but it's pretty unlikely, and I'll show you. So we need to know what sort of life we're looking for. And you're going to learn that life out there most likely, almost certainly, is going to be carbon-based. So we've got to be on the lookout for it, but keep an open mind. So why is it carbon, and why do people often raise the issue of silicon? People often say in a discussion, how about silicon? And the reason is they're both in the same column in the periodic table, which means they've both got 4 electrons in the outer shell, so they can form 4 separate bonds to form long, complex molecules. And life needs long, complex molecules. The most simplest of life on Earth is complex. Life needs to be versatile, it needs to be strong, and it is quite complex. So both carbon and silicon has those 4 separate bonds, which make them very versatile. But that's where the similarity ends. I'll show you. We're going to discuss these 3 in a bit more length now. Carbon is much more abundant. You'll see that carbon bonds are much more stronger than silicon bonds. And you'll also see that carbon oxides, importantly, are soluble in water, where silicon is not. So let's look into these. So here is your top 8 elements in the universe and the galaxy and so on. And you'll see I've highlighted carbon and silicon. And you'll see here carbon is 10 times more abundant than silicon in the universe. You might argue there's a bit more silicon actually on planet Earth. Most of it's tied up in rock. Carbon is far more accessible. But in the universe, carbon is 10 times more abundant. The prime reason for that is carbon primarily comes from low to medium mass stars. They get up to a point where they produce carbon and oxygen. That's as far as they go. They don't produce silicon at all. They are much more common. It's something like 85% of all stars in the Milky Way are low to medium mass stars that are capable of producing carbon but not silicon. The stars greater than 8 solar masses that go supernova, that produce the silicon and then disperse it, make up about 1% of the stars in the galaxy. So it puts it in perspective. So there's some good grounding reason why there's far more carbon. And there's one thing that we always learn at university. The commonest things occur commonly. It's always a thing in life. And carbon is 10 times more common. So carbon bonds are much stronger. And remember, we want versatility. We've got that with those. But we want strength as well with our complex molecules. And here's just a very basic, crude diagrams here. Here's carbon with its nucleus, with its 12 particles, and then it's got its nuclei around, and you notice there's 4 in its outer shell, 4 electrons. Silicon's got 4 in its outer shell as well, but because of its higher atomic number, it's got another shell in between it. Its outer shell, that where its electrons form its chemical reactions with, is 1 level out. And of course, negative electrons are attracted to the positive nucleus. They're in there more snug. So it's the outer shell of the electrons for chemical bonding is much closer to the nucleus in carbon. So those bonds are naturally going to be stronger. Furthermore, because of that, and I won't go too far into it, but there's electron orbits. We talk about orbits very loosely, but all you're really describing is a space where you're most likely or probably going to find that electron if you go looking for it. And there's different shapes. There's the S shape for spherical orbits, and then there's a P, like 3 lots of dumbbells, if you will. P orbits. And just for you more technically minded, because you're closer to the nucleus, the lobes of your P orbits are much smaller and they overlap each other a lot stronger. And it's for that reason that carbon can form double and triple bonds with itself, which silicon, it's not so easy to do with silicon because those P orbits are so much bigger and they can't overlap so well. So carbon bonds are much stronger, which allows stable and longer complex molecules, which, as you'll see, life requires. And you're going to see some diagrams shortly that you'll see. Okay, and I put this diagram just to explain that principle, how important it is. So most molecules have a scaffolding or a central backbone or scaffolding, if you will. And here's one here with a nice a carbon hexagon here. And you've got an OH group. And this is the reactive group. So often you'll have your main thing here, but your reactive little bit on the side that's involved in the chemical reaction. And that chemical reactions usually involve quite a bit of energy, usually in the form of heat with another chemical, to break that bond. But when you stir things up and you start breaking bonds, you want that bond to break, enough energy, but you don't want the rest of the scaffolding structure to break up. And carbon bonds are strong enough whereby you can have chemical reactions with a chemically reactive group, if you will, attached to the side of the main scaffolding or backbone. That scaffolding and backbone will remain in place while you go having your chemical reactions. A lot of reactions like that, silicon couldn't handle it. The whole lot would just fall apart because its bonds are too weak. They would fall apart. Okay, and the next point is carbon oxides are soluble in water. And you might think, oh, okay, so big deal. Oxygen is the most abundant element in the universe, just after hydrogen and helium, which of course doesn't count because all it is, it's not reactive. It doesn't react with anything. It's just good for party balloons and for cooling MRI scanners, actually, too. They use helium for that. But apart from that, it's a non-reactive. It's an inert gas. So it's highly reactive with carbon and silicon. Put the two together and they'll hook up quite happily. Carbon oxides, like your carbon monoxide and carbon dioxide, they are soluble in water, so water-soluble gases. So they are available for metabolic chemical reactions. They're quite happily to be cruising through your body. Admittedly, arguably, you wouldn't watch carbon monoxide flow going through you. But you get the gist of it. Silicon oxide, solid. It's rock, essentially. You can't have rocks floating through your bloodstream, so it's not suitable for metabolic reactions. And I believe there was an episode on Starship, on what's the thing called Star Trek, and they went to some foreign planet where there was silicon-based life, and there was some illness going through it, and they asked Dr. Spock, could you go down there and help them? And he said, I'm a doctor, not a bricklayer. So I hope I've convinced you that if we're going to be looking for life elsewhere, we don't want to have our blinkers on, but we're more likely to discover something related with carbon chemistry. So the conclusion from there is all life on Earth, all life is carbon-based, and will be likely to be carbon-based elsewhere as well. Likely to be. Nothing in this world is certain except uncertainty, so don't put the farm on it, but most likely it's going to be carbon-based. So that next raises our question. So, okay, so that we've got a gist of life now. We've got some two basic sort of considerations. We've got the ideas of what life's about. We know it's likely to be carbon-based. So let's continue our journey on Earth. How did life on Earth start? Then how did it get going and evolve? And we're going to look into these three things to try and address these questions. We're going to look into essential ingredients of life, the essential building blocks of life, and then we're going to talk about creating life, how it got underway on Earth, where it likely got underway on Earth, and when it got underway on Earth. And this is all relevant to where we're heading, looking for Earth 2.0. Okay, so here's our top 11 abundant elements from hydrogen down to phosphorus. These 6 here, so they're in the top 11. These here are all critical elements for the cells of life. They're the critical ones. You might argue, oh, how about calcium? How about iron? Yeah, they're for calcium for your bones and iron for your hemoglobin and stuff. Yeah, they're all specialized functions. But your critical ones for all the functions of all the essential for all of life, these 6 here are important. All of them, as you can see, are abundant throughout the universe, and all of them go to make up these 4 key building blocks of life, which we'll talk about. And these are the 4 key building blocks of life here. First is what we call nucleic acids. We're going to go through them, but we're going to talk about nucleic acids, proteins, lipids, carbohydrates. And something you will see here too is these are all based around long, strong, complex carbon structures. I can't emphasize that theme which should be going through your mind the whole time. So let's look at nucleic acids, and that of course is your DNA and your RNA molecules, and you're probably familiar with the double helix, the famous double helix structure of DNA and the single helix structure of RNA. The DNA, of course, is very important for storing genetic information, and your RNA is important for getting that information, transcribing it, taking it to the ribosomes, which are RNA-based, by the way, as well, and then translating that into a series of amino acids for your proteins. So really, they're important for your metabolism, growth, and reproduction. All that genetic information for that is all stored in your DNA. You might think, well, RNA does a heck of a lot. It's capable of storing information. Why not RNA? RNA is more versatile than DNA, but DNA is more stable. And we're going to address that a little bit more, probably another 10 or 15 minutes time. But you can see, look how complex. When you see these hexagonal and pentagonal sort of shapes here, at the center bits, there's always carbon at the corners. So there's carbon, carbon, carbon everywhere. There's loads of phosphorus in there, nitrogen, and so on. Okay, the next one are proteins. Proteins are large and complex. They are the workhorses, if you will, of the human body. Everything's really hinges on proteins. There's over 100,000 protons in a human being. They're really important. So they perform most of the work in the cells. They're involved with metabolism, creating the structures, the physical structures and framework of life. They're involved in transporting nutrients and various things around the body, and they're involved with us growing as well. They are made of amino acids, and here's another interesting factor, is that there are about 500 natural amino acids, only 20 that all of life, right across the spectrum, all of life on Earth uses only 20, the same 20 amino acids. And another little thing too, there's chirality, there's a concept called chirality. It's an orientation of molecules, and a good analogy is your hand. See, my hand now is they're both identical, but the mirror images, they're not the same, left-handed and right-handed. And amino acids So you can get them left or right-handed. All the amino acids life uses on Earth are all left-handed. No right-handed amino acids. So they could be elsewhere, but as far as we're concerned, all amino acids are left-handed. So that's another little theme going on. That sort of life's got this universal core of machinery going on underneath everything. And that's important for where we're heading. So that's there is, by the way, you probably saw that diagram there, yeah, just to point it out. All that, that's a typical sort of protein type of 3D structure, and all of that in red is carbon. Everything you can see just carbon, carbon, carbon. And it's those strong carbon bonds that are holding structures together like that. So yeah, fats and metabolism. So lipids, rather, which fats and form fats and membranes. Lipids are important. Lipids are the key that make up our membranes. Remember we learned early on how crucial membranes are to the whole thing about life. And lipids will form quite happily into these, and I'll show you shortly in a diagram, they will quite happily form into these membranes on their own. So they're very important and they store energy. Once again, they are made up of those 6 essential elements. Carbohydrates, which means all your sugars and so on for energy. You've got glucose for your quick energy. You've got also stores energy. There's glycogen, that's like a form of carbohydrate for storing energy in your body. And then there's the universal currency, ATP, adenosine triphosphate. You're going to learn shortly how that is life's universal energy currency. Once again, another little common theme. You might think I'm on repeat all the time, but this is important. There are so many things in life. And of course, that is totally made up of all those 6 and crucial elements there. And incidentally, ATP is actually got a ribose sugar in it, which is important. Okay, now all life uses the same DNA, the same RNA, it uses the same amino acids, the same 20 amino acids, all left-handed, uses the same lipids, uses the same sugars. All 4 of them, there's 2 things I want to mention here. First of all 4 of those, as you'll see shortly, can be formed in abiotic, in other words, pre-life reactions. You don't need life. They can all, in pre-biotic or pre-life conditions, all 4 of those main things can quite happily form. I've mentioned here all life uses ATP as its energy currency. So that suggests that life on Earth came from some common ancestor, universal common ancestor. And that has implications in the search for extraterrestrial life. One is it gives us a model of a fundamental, there's some sort of fundamental or core machinery that's certainly on life, on Earth anyway. There's this core fundamental thing that's going on that we've diverged from there. So that tells us that maybe, it's a good start looking for these fundamental things on other planets as well. But also it's telling us not to keep our blinkers on. Because if you have got this one core fundamental thing that we've all, with a common ancestor that we've all branched out in the diverse life you see on Earth now, maybe on another planet they had a similar concept, but that universal common ancestor, slightly different, branched out totally different with a different set. So it tells us twofold what to look for, but also, think outside the box as well. So interesting implications of that. So let's look at creating life on Earth. How, when, and where did it happen? So, how did life's building blocks form from non-living chemicals? And the first thing is, where did they come from? You might ask yourself. Probably twofold. Where did they actually form? Twofold. One, possibly on Earth. Earth was pretty barren initially, but also had all the right conditions for the building blocks to form. It had tidal pools, that's big tides into rock pools essentially, swishing them up, bringing water out, going back down again, giving it dry, wet periods. Clay surfaces, I think coming up shortly I'll show you how important clay surfaces are. Clay surfaces can be very sticky, so it can pull chemicals in together, can concentrate chemicals. There are minerals implanted in clays that can act as catalysts, in other words, enzymes that speed up and potentiate and facilitate chemical reactions. We'll talk about hydrothermal vents shortly. Ultraviolet light as well. The ultraviolet light from the sun was a lot more powerful in these days, way back then in the early stages of Earth. So there was a lot going on there. In fact, there's a very famous experiment in the 1950s by Miller and Urey, whereby they got a vessel, a glass vessel, and they put in there some water vapor, ammonia, methane, and some hydrogen gas. And then set through some electrical discharges through it to mimic lightning. And after a week, they thought, we're getting all this slime down the side. They generated amino acids in the laboratory. And of course, that's the 1950s, so 70 years ago. They've got a lot, trust me, they've got laboratories, they've got biochemistry, has got so more advanced to do it and far more. But that was a very famous first experiment to show that. Possibly some of these building blocks might have not formed on Earth, but come from outer space somewhere, like on comets and asteroids. And indeed, on asteroids, recently, asteroid Bennu, they have found many amino acids, they have found many organic compounds, they've found all 5 of the nucleotide bases that go to make up your DNA and RNA. All 5 of them were found on recently an asteroid Bennu. So they're out there. There's also the concept, going one step further, of panspermia, that possibly even life started elsewhere and then didn't have to form on Earth, but it came to Earth on a comet or an asteroid. That's another thing. But either one of those two things, no matter what you may think or believe in, whatever, it's kicking the can down the road, isn't it? It's not answering the question how life got started, whether it was here or Mars or wherever, how life got started. So, but those are 2 schools of thought. That did it form here on Earth, or did it get formed down the road and then just came here? So what do we know already? And this is what I was just alluding to, then I realised it was coming up when I was talking about lipids. Lipids readily self-form into membranes, in fact spherical membranes. And the reason being, they are structured, they have a hydrophilic, a water-loving head, and they have tails hanging from them with their structure, which are hydrophobic, disliking of water. So you get a hold of them, start lining up, and you'll see they'll arrange themselves. The hydrophobic bits will all stick together because they don't like water in a solution. The hydrophilic areas will naturally form on the outside, and you'll get this bi-layer sheet forming that then will naturally form into a spherical thing here to create a membrane or a prebiotic cell, if you will. That will happen naturally. You can do this experiment in your kitchen when you get home. Get a clear bowl of some warm water, get some dishwash liquid, make sure there's no too many additives in it. Any brand you like, Pam's will do. Put a few little drops in there and you'll see little spheres start forming in the water, in the warm water. And that's just lipids just naturally forming nice little spherical membranes. Amino acids will assemble quite happily into proteins. I mentioned how you can make amino acids, mixing together with some ammonia, some hydrogen, some methane, and so on. You can actually make amino acids. Well, amino acids in the right conditions in laboratory, in fact, even without the laboratory, you can form into proteins. They will form into very primitive, but they will form into proteins. Your RNA, which is related to your DNA, which carries your genetic information involved in forming your proteins and so on. So that's crucial for life. That can form on the surface of clays. As I talked about, clays are nice sticky, so they attract and concentrate chemicals. They have minerals on them to assist chemical reactions, and they have shown that RNA, you get some clays in the right conditions, RNA can also form without life. And there it is, also linking the bases together as well. I didn't see it a little bit down below. So it'll also, the clay will bring together those nucleotide bases, link them in together to create an RNA molecule. And as we'll look at shortly, RNA is the next stage before DNA. So yeah, this is it. It's called the RNA world hypothesis. You saw how complex DNA is, and DNA is great. It's got all the genetic information, and its advantage is it's nice and stable. But as I also alluded to, RNA also carries that information, but you don't want it long-term because it's not stable. But you can see it's a stepping stone in the formation of life. There's a theory called the RNA world hypothesis, how life may have got started before they started evolving into complex cells. Everything starts simple and moves up from there. So it proposes that the RNA was the first self-replicating molecule. It can occur naturally. It's much simpler than DNA and many proteins, which is an advantage because it's easier to make. It can store genetic information. It can self-replicate. It can do the job. And it's also capable of forming the very early proteins, leading to the evolution of more complex proteins and the more complex and stable DNA. And you're going to learn shortly that this all takes millions of years, but it's all plausible. It can all happen. So continue on with what most likely happened. How do we go from these simple bacteria up to the more complex bacteria and onto more advanced cells from there? And this is a nice little statement I've written down here that you commonly see. And it was a guy, when they were talking about how life can form with prebiotic reactions, and there was a famous British astronomer called Fred Hoyle, and he sarcastically said, so are you telling me that essentially you just had a junkyard full of nuts and bolts and a tornado came through, poof, and within a minute later you had a jumbo jet fully assembled? No, just what a stupid what a silly sarcastic comment. No, what the scientists will tell you that current day, even the simple current day bacteria did not arise spontaneously. Science does not say that. It arose from very simple life forms, small multiple increment steps, countless interactions, countless combinations. Some failed, some worked, some didn't, some collapsed, and so on, in multiple places over millions of years to get to the most simplest of simplest forms of life. It was a long, complicated journey to get there. And I've put multiple places because there is some evidence suggesting that life just didn't get started somewhere and just sprung out from there. There are suggestions, a lot of evidence and very sensible thinking that life might have got started, got wiped out, might got it going over here, got wiped out, might got it going over here, got wiped out. Conditions were pretty harsh. And as time went on, one of those little pockets of new life, because it appears that life can form quite readily. And it did form they're saying readily, but just kept getting snuffed out. But sooner along the way, it just got going. So it probably goes multiple combinations, multiple places over millions of years to get to the simplest form. It didn't happen overnight. So that's how life may well have got started on Earth. How about where? And there's two prime locations. One is in these tidal pools, or rock pools if you will, and two hydrothermal vents. The pools are great because tides come and go, so you get wet and dry cycles to help chemical reactions. You've got ultraviolet light, and as I mentioned, it was more intense at that time in early Earth to give the energy to drive chemical reactions. Very diverse chemical inputs. You had stuff coming in from the land, from the water, atmosphere and so on. So a lot of chemical inputs, and you had that important clay. That's great. It's sticky. It pulls things together. It links chemicals together. It acts as a catalyst as well. Clay is important. And then there's vents, and there's three types of vents. Underwater vents. You see them, you've probably seen, they've discovered more and more of them over the years as they explore the bottom of the ocean. In the deep sort of ocean trenches, they find them, and we get this hot water just spewing up into the lower parts of the ocean. And there's three types: there's black smokers, white smokers, and alkaline vents. Your black smokers and your white smokers, the temperatures are too hot and there's too acidic conditions for early life. They're teeming with life now. There's life called certain types of archaea are known as extremophiles. You've probably heard of them. Some of them can live in really hot or really cold temperatures, or some actually, like tardigrades, can actually handle radioactivity. You've got some that can handle strong pHs and so on. They're modern day extremophiles, so don't confuse them with early life. But early life couldn't have handled them. But your alkaline vents, the bottom of the ocean, nice temperatures, much more moderate temperatures, neutral pH, and that's a good place for life to have was formed early on. It's a good place to have formed. Continuous heat, a lot of chemicals coming up and minerals coming up from below. Ultraviolet protection, I've just mentioned it's a good thing. Ultraviolet in those days was strong. It can be good for chemical reactions, but can also be harmful for life. So, and it'll come down to the next comment, but it might have provided, being deep down in the ocean, some protection against too powerful ultraviolet light. And microchambers, what I mean by that, and I've mentioned already how important, how crucial it is that life has a membrane, that it has a little cell, a basic unit, to isolate it from the more harsh external environments. You've probably seen, you can see small ones here coming up in these hydrothermal vents over here. There's little chimneys, there's little white chimneys up there of structures coming up. And these alkaline vents, you tend to have these nice little chimney structures. And those chimney structures are full of little microscopic little chambers in them. And those microscopic chambers would have been ideal for prebiotic sort of cells, pre-living little environments that cells might have formed in. Get the chemistry going. They would have acted as a membrane for chemicals to get concentrated in there and quietly taking in the warmth, taking in all the minerals and the nutrients, but being protected. So that's another nice little niche where life just might have got going. So it's thought, combining those two, that probably there's every chance that life occurred initially in these alkaline hydrothermal vents at the bottom of the ocean. They then, as they got stronger and adapted more to the surface conditions, where they were able to come up to the surface more and start growing and developing more from there. So that's where they think most likely candidates where life would have got going. So how about when? That's what they start looking at the rocks and the fossils. And the key message here is that life got started early on Earth. That's where the evidence points. But conditions on early Earth were pretty extreme. You know, the first few hundred years, it was just a molten surface. You had what we call the late heavy bombardment, that stage. That's where the Neptune and the large planets ploughed into a whole stack of rubble in the outer solar system, showered the inner solar system with lots of rocks and debris, comets and asteroids and so on. So it was a pretty violent sort of place, and life wouldn't have been conducive for life to develop, wouldn't even have for life to continue for that matter. But slowly the Earth would have cooled down and the first oceans formed and so on, and this late heavy bombardment phase would have dampened down as well. But as I mentioned, it would have got started early, but it was a long process because it just doesn't get up and going like that. It's a long, slow process from just a world that's habitable. In other words, it can support life. You start getting all this prebiotic chemistry going on, prebiotic environments and so on. You start getting little vesicles, that's sort of like little pre-life cells, and then little proto-cells, not fully mature cells, but over millions of years, all this starts developing, getting simple life, then to Luca. And that's the last universal common ancestor before you get this diverse of life over billions of years. But this would have taken probably maybe hundreds of millions of years for all this to have happened. Long series of steps early in the Earth. And that's what the rocks tell us. So we're going to go into this a bit of detail, but just up front, life appears, quite possibly could have been established 4.1 billion years ago. In other words, 500 million years, or 500 million years after the Earth had formed. So we're going to now look at some milestones of life on Earth. So here we go. We've got long here, we've got billions of years. The first 100 years, let's put Earth in here. Earth formed about 4.6 billion years ago. And for the first 500 million years, or 500 million years, it was pretty hostile, sort of bare rock place. It wasn't conducive to life. And then just before I start putting in some more figures and stuff here, I want to introduce you to people who say, well, how do they know all this sort of stuff? The answer is in the rocks, in particular, zircon. Zircon is the perfect rock or mineral, if you will, for it. So this is what zircon looks like, and zircon is a form of it's a mineral, forms a rock, and it's made up of zirconium, silicon, and oxygen, and it's got some very unique properties to it. Just briefly, it's the oldest mineral that's been known. The oldest zircon, they've dated at 4.4 billion years ago. Old. That's, in other words, when the Earth was only 200 million years old. So that's what they've dated back to. It's sort of the oldest rock/mineral that they have found. And there's three really important properties about this crystalline structure mineral called zircon. It traps, as it solidifies, it would have been liquid, as it solidifies into this crystalline structure, it traps other things around it, whether it be microorganisms or chemicals or other elements. It traps them in it. It retains them. Once it's solidified, nothing in, nothing out. But it's durable. It's extremely durable for weathering and chemical. So physical weathering, like water and wind and so on, but also chemical weathering. It is very, very durable. It's, 4.4 billion years. So its crystalline nature retains a lot of things, but importantly, it retains radioactive elements, in particular uranium. And uranium decays into lead. So when it solidifies, it allows uranium in, but it doesn't allow lead in. It just only allows uranium in terms of those two elements. So when you analyse it in the laboratory, you see how much uranium, you see how much lead is in it, and you don't have to wonder about, oh, how much was already there. No, whatever lead is in there has been from decay of the uranium. Thank you very much. Nothing in, nothing out, once it's solidified. So it's a very unique sort of mineral that's just, just perfect for a geologist. So the zircon suggests Earth had oceans about 4.3 billion years ago. In other words, when the Earth was only 300 million years old, water. That would have been most likely, well, there's different sources. I do a little bit of a talk on that, but a lot of it would have come from comets, and so some of it would have come up from water vapor being outgassed, but that's, we won't worry about that. It's another talk. But had oceans, you might say, well, how did they tell that from zircon? They're able to look at, for example, the oxygen in the zircon and look at what isotopes. And we've talked about isotopes in the past. Just means you've got more neutrons in its centre. And I expanded. That's the purpose of the handout. I can expand on little things. It talks about isotopes. But needless to say that there's two isotopes defined by that differ by the number of neutrons in their nucleus. There's oxygen 18 and oxygen 16. And they found an unusually high ratio of oxygen 18 to 16 in the zircon. Oxygen loves to react with things. And when the oxygen water reacts with rocks, you tend to get development of the more oxygen 18 isotope. So with an unusually high ratio of 18 to 16 isotope ratio with oxygen, that tells you that there's only one thing that would have done that: water interaction, rocks with water interacting with one another. So that's interesting. So they put that there at about 4.3 billion years ago. Then the first life forms. Now this is what I call soft evidence. You'll see why in a minute. But life possibly could have got first life formed by 4.1 billion years ago. How do they know that? Because they found some graphite grains. You know, graphite is carbon, compressed carbon, and some graphite grains trapped inside the zircon. And they found an interesting ratio of the carbon isotope ratio, a really high ratio of carbon-12 to carbon-13 isotope. Life has a preference and a bias for carbon-12. It's lighter, it's smaller, it's easier for the cell, for the membranes within the cell and so on, and also for metabolic reactions. It's just easier. Life prefers to deal with carbon-12 than carbon-13. Has a preference. So when you do see high number, that is an indication that probably there was some life around pumping out more carbon-12. Now you might say, yeah, so it wasn't a direct fossil. It's what they call a chemofossil, not a direct fossil. Oh, look, here's some remnants of some sort of microorganism. No, it's just sort of indirect evidence. So it's not universally taken because it's not solid, but food for thought. So there's some soft evidence that maybe life could have been just getting underway about 4.1 billion years ago. So we've put that in there. Now, and then we get into the more harder evidence, microfossils. Actually, in the rocks, actually see fossils of early life. And they appear to be, there's a first group of cells called prokaryocytes, very simple type of cells. They didn't have a cell nucleus, just a single strand of DNA floating around in the cytoplasm in a membrane. When I say very simple, relatively simple. Life, remember, is complex, even the simplest life. But this first relatively simple life probably came around about 3.5 billion years ago. That is a lot harder evidence. There's actually some fossils in the rocks, but also there's these things called stromatolites. I think I've got a picture. These sort of rocky formations here in South Greenland, Western Australia and South Africa. I think they've got these little stromatolites. Stromatolites are a rocky formation, and they've formed from microorganisms. And there was one of the type of microorganism in the early days was cyanobacteria. They're still around today. Cyanobacteria were known, they were able to secrete a sticky substance over the layer of the top of them that would attract and stick down sediment, sort of grains of sediment on them. And cyanobacteria were one of the first bacteria that evolved to perform photosynthesis. It liked the sunlight and got energy from the sun. So it naturally wanted to move upwards through that layer of sedimentary rock, closer to the sun, got up above the sun, started doing its things, producing sticky secretions. Sediment rock settled on it, and the process continued to get these heaps and heaps of little sort of micro-layered rock formations called stromatolites. And So they are also an indication of cyanobacteria. That's a living thing. Only cyanobacteria can form these stromatolites. And there's, of course, the fossils of the microfossils within those. And they date those back to about 3.5 billion years ago. So that's a lot harder evidence. I think that is the accepted, even the skeptics accept, yeah, 3.5 billion years ago, definitely life was here. Then larger, simple, still simple single cellular eukaryotes came along. We're all made of eukaryotes. It's just another chain in the evolution. Eukaryotes are a lot more advanced and sophisticated. They've got their DNA, nice little double helix curled up into chromosomes. Inside a nucleus, it's got a separate membrane. They've got mitochondria, Golgi body, and all these other sort of little miniature organs called organelles inside them. So they're a lot more sophisticated, and it enabled more evolution down the line. And it probably formed from an archaea, it's a large prokaryocyte, engulfing a bacteria. The two of them lived together quite happily in unison, and the bacteria decided, oh, we can happily live here as well. We're enclosed by membrane. That became the organs inside the larger cell, became the cell nucleus, mitochondria, and plants have developed into a chloroplast, for example. So that's probably how that got started. A lot of evidence for that. So that got started about 2.1 billion years ago. That's the type of cells that allowed life to get complex and form us. Then about 1 billion years ago, those simple but still single cell eukaryotes, they then found, oh, let's join up together. Still simple, but multicellular organisms like algae and fungal came along. And only as recent as 300 million years ago, you started getting plants and animals like fish and stuff. Vertebrates started first appearing 300 million years ago. Humans, our early ancestors, Homo sapiens, came along about 200,000 years ago. Here's food for thought that I worked out. So if you put this into here it is, yeah. So the main condition, life got underway as soon as conditions were suitable. Life got underway pretty early. But life was simple cellular for over 3 billion years before becoming complex. That's important. So that's the thing there. Life gets underway pretty quickly. It doesn't take too much, but it takes time, and it takes time to get complex. Now, I put this into a cosmic calendar. I went 3.6 billion years and worked out how many seconds that would be and so on. If you squash it down, sometimes you see this exercise with the whole universe, the age of the universe. So I put it down to 4.6 billion years for the age of the Earth. If you put it in the cosmic calendar, where Earth came along the 1st of January, midnight, the 1st of January at 12 a.m., just 1 minute past midnight, say, and went right through day after day, month after month, week after week, day after day. Do you know when life on Earth was simple slime until the 10th of October? If you squash that into a year. Do you know 200,000 years when humans first showed up? 20 minutes before midnight on the 31st of December. That's when we turned up, if you put the whole history of the Earth. Who do we think we are? Yeah. Well, I'm sure I don't mean to offend you, I'm sure you're very important, but there you go. Puts us in perspective, doesn't it? So, conclusion of the origins of life is the ingredients for life are universally abundant. I've shown you that. I've shown you that creating and assembling the building blocks of life, yes, it is plausible. Given time, life can form, can evolve, and as you see, it can flourish. I think there's up to about 8 million, I think, species on Earth. They've identified 2 million. Life started on Earth early, but remained simple for over 3 billion years. And we turned up very late. So, putting that in the context of what we're trying to do, look for Earth 2.0, life will likely be widespread out there, but it will be most likely simple, single cellular life. Intelligent, complex life, it must be out there, but it's going to be pretty rare, just by a numbers game. I heard even someone say too, if humanity's not careful, if it misuses its 21st scientific technology, history could recount humanity as being nature's brief but colourful experiment with proto-intelligence. In other words, we can come and go too quite happily. So let's move on from there. So that's our first chapter. Conditions. What does life require? In other words too, if we're going to be looking for life, it's going to be, first of all, look for planets that have got all the conditions for life. Life's could be quite elusive to see. So what should we be looking for seeing a planet that's capable of supporting life? And there's 3 things that life wants or needs: liquid water. It needs liquid water. It's a perfect solvent, but it needs it for dissolving and transporting nutrients, bringing it into the cell, transporting it through the cell, metabolic reactions to facilitate metabolic chemical reactions. They usually all involve water, but also, as we mentioned earlier on, to get rid of waste. You need to dissolve waste in water to expel it. Compounds in chemistry. You need those to make and assemble your essential building blocks of life, your proteins, your lipids, your carbohydrates, and your nucleic acids. You need energy, whether it be in the form of sunlight, whether it be in the form of chemicals or heat, but you need energy to drive those metabolic chemical reactions. So a planet needs to support life. Those things there. It's got to have those conditions as far as we're aware. So the next thing is, where and how should we be looking to find these conditions next? And there's these sort of 3 or 4 considerations here, which we'll go through each one. We're going to be, where are we in the galaxy? What sort of planet? Where is it in relation to the star? And what sort of star should we be looking at? What sort of host star? So yeah, it's not all equal in the galaxy. Just there's a nice little zone in the middle of the galaxy where it's most ideal. And here's our sun here. But there's a middle region where it's most ideal for planets to form. Let's have a look at this. So in the inner regions, it's very dense. There's a lot of star formation going on, a lot of big stars, massive stars. So you're going to have a lot of supernova explosions, gamma ray bursts, that sudden just bursts of high energy radiation and high-speed particles after a supernova explosion. So that's going to be huge amounts of sterilizing radiation to destroy any atmosphere, radiation to tuck in, destroy any life. Frequent star formation is going on with large stars, which leads to high metallicity. Metals in astronomy is any element heavier than hydrogen and helium, and in other words, carbon and not oxygen, carbon, and so on. They're all made inside stars. So the more generation, if you're going to have lots of big stars with short lives, go supernova, you're going to have lots and lots of these metals, these heavy elements form. So you're going to have high metallicity in this region. High metallicity leads to a bias for the planetary system of gas giants. The logic behind that is you've got lots of metals, so your rocky core can form really quickly and get big to a critical size, or it can start pulling in the hydrogen and helium around it. So it creates a big gas giant. As opposed to low metallicity, things happen very slowly, and by the time you've got up to a certain rocky size, the gas has dispersed itself anyway, so you're left with rocky planets. So it's going to lead to gas giants. Gas giants are not ideal for life, as you're about to see. Because it's a crowded environment, you're going to get a lot of chaotic gravitational interactions, planetary systems. Again, it's going to be chaos, a lot of disruption going on. So that's not ideal. You move out into the outer regions there, you're going to have insufficient metallicity. It's too sparse, where it's not going to be so conducive perhaps for planets to form. Also, you've got less dense gas density for stars to form in the first place. So your sweet spot is in the middle, where you've got stable orbits, low radiation, and you've got sufficient heavy elements, just the right amount to get these rocky planets going on. So that's called the habitable zone in the galaxy. Okay, then you want a rocky planet. Of course, a gas giant doesn't provide you a solid surface. You're going to want a solid surface to start concentrating and bringing chemicals together. And with these exoplanets, as we learnt last month, they can determine the size by the transit method, by photometry, the mass of one of these exoplanets for spectroscopy, how much it influences the wobble of its host star. So they can work out the density from it from there. The mass range, you want an exoplanet between 1/2 and 5 Earth masses. Anything less than that, you're not going to hang on to an atmosphere. Anything more than that, and you're just going to be gathering in too much atmosphere, and you're going to essentially become a gas giant with a rocky core. Plausible size range, anywhere from being able to estimate computer models, about 0.8 to 1.8 Earth radii is ideal. So that gives you an idea of the mass and radii. As mentioned before, with an atmosphere, you want an atmosphere to keep liquid water, but for also life to respire, support life. So atmospheres are detected and they're analysed, which we'll talk more about that next month. We're going to talk about spectroscopy next month. We're going to talk about that, and I'll touch upon a little bit now, but the James Webb Space Telescope has been very good at identifying whether one of these rocky planets has an atmosphere by looking at the light that gets filtered through the side of the planet that's got an atmosphere by the host star. And that's just an idea, just gives you... I picked this one because it's a off a gas giant, but it's nice, you can see this is spectroscopy. That's the peak of carbon dioxide, water and so on. So you see these little rises here, that's the amount of light's being blocked in certain wavelengths. Here's your wavelengths of light, and that's the amount of blockage, and that's sort of some James Webb data there. So when they see that, they know, hello, we've got an atmosphere, there's water and carbon dioxide in there, and that's off, it happens to be off a gas giant. But I put that one there because it's a nice, easy to see the big humps there of where barnacles in the atmosphere. So they're able to detect atmosphere very well with the James Webb. Now, also, there's a habitable zone around stars. You may well have heard about that. And that's the position or the distance of the orbit from its host star, whereby the temperature is just right for surface liquid water, on the understanding you've got an atmosphere, of course. Whereby if it's too hot, if you go inside that area, it's too hot, if you're too close, and the water's going to boil away. Too far out, and it's going to freeze into ice. But there's that habitable zone. And of course, with different size and temperatures of stars, it's in a different position. So cooler stars, that habitable zone is a lot smaller. It's closer into its host star, and it's smaller. Sun-like stars, say middle of the road, it's out a bit further and a little bit larger, a bit more leeway. And as you go out to big, giant, hotter stars, it's much further out and larger. And that makes sense, doesn't it? That sweet spot is moving out. But it gets bigger as well as you go out. Now, the ideal host star, they don't just think, oh, if you've got a pick of stars, where should we start? What sort of stars should we look around? And yes, so stars spend 90% of their life in what we call the main sequence. Nice, relatively stable state, fusing hydrogen to helium at their core, by definition, and that's their stable state. The last 10% of their lifespan, they swell up to become red giants and red supergiants, and they are very unstable states for them to be in, relatively unstable, and that's the last 10% of their life. So it's your main sequence stars is what we're after to be looking at. Let's bring that up. This here, so your main sequence stars, they are then broken down to different groups, and they're called spectral classes. They used to go A, B, C, D, E, according to the hydrogen spectrum. We're going to learn all about that next month. But for historical purposes, they reshuffled them around to make sense of it all. And you start from really small, cool and dim stars to large, hot and bright stars. They come in a wide variety here. Our sun is what we call a G class. It's sort of roughly in the middle there. That's where our sun sits. So these F, A, B and O class stars, they are too short-lived. If you want a star, you want a star that's going to offer a steady, because it'll be stable, with a steady range of temperatures, just nice and relatively stable. And you want a star that's going to be living a decent length of time as well. So the F to O class are too short-lived. Life won't have enough time to get moving. They only live their lives in millions and very few billions of years. Furthermore, a lot of high energy radiation. It's going to wipe out any atmosphere or be destructive to life. And they're very rare, whereby all these here, you're only talking about 1 or 2%. These two here are less than 1%, and these ones here are only about 1% of all stars. They're really, really rare. Life has a bias for lots of small things and fewer larger things. Whereby your M class, which are your red dwarfs and some of your Ks as well, they are long to live, and that's what you want. You want to give life time to move along. They make up 75% of all stars in the galaxy, are these tiny little M dwarfs. But there's a catch. Very frequent, intense superflares. Just because of the nature of them, they have a lot of convection going up and stuff going on. They're essentially boiling away, if you will. They're feisty little things, and they give out frequent, intense, really sort of like solar flares on steroids, really intense blasts of energy, which would not be very good, be not good radiation for an atmosphere of life. And the other thing to add there is the habitable zones. Remember, small stars, small cool stars, habitable zones in a lot closer to them. So the habitable zone where you're going to get liquid water, if you've got an atmosphere, still after your radiation, that's going to be very, very close, so it increases the amount of radiation, but also introduces the concept of tidal locking, where if you get two bodies that are just close to one another, particularly a smaller one to a bigger one, the smaller one first, but they both eventually gets what we call tidal locked, and we see it with our moon. The rate of rotation of that object it turns into synchrony with exactly the same rate at which it orbits the larger object. And our moon, it rotates roughly every 28 odd days, and it takes that long to go around it. So the same side always faces us. So it's a big challenge for life, not impossible, but it's another challenge for life. If it's on a star, so if you get an exoplanet around an M-class star, sure, long lives, very frequent, but they've got these super flares going off, and you're tidally locked. There's every chance to be in that habitable zone. You're so close, most of those planets are tidally locked. One side constantly facing the host star, getting blasted with radiation, and the other side constantly facing out to the coldness of space. All sorts of computer models come up. Well, maybe there's a chance you could get life-suitable conditions on the Terminators, something like that. So it's not all black and white, but yeah, it's just another challenge for life. And it's these classes here, your K and G class, remember our sun's G, which are ideal. They've got relatively long lifespans, between 10 to 70 billion years. Our sun's 12 billion years, full lifespan. They make up a decent 20% of all main sequence stars, stable energy outputs, habitable zones that further bit out more conducive to life. That's your sweet spot for your host stars. So let's move down to signatures. So we now know what does life require. We know what we're looking for roughly in terms of the star. We're in the galaxy. Whereabouts should the orbit be? What should we be looking for? Should we find one of these exoplanets? Think, are we looking at Earth 2.0? What should we be looking for? First of all, as we've talked about, a rocky planet between 0.8 and 1.8 Earth size, with an atmosphere, around a habitable zone, ideally around a G or a K class, spectral class main sequence star. That would be the sweet spot, if we're looking for Earth 2.0. Also going to be looking at signatures of life, what we call biosignatures in the atmosphere. So let's look at these. This is just a thing from Kepler, and they've actually got the M class in here as well. And from all the more updated data, but they've got little charts like this come out. To date, I think it was early last year, January 2024, it was 59, I believe. That's gone up to 67 now. Confirmed rocky exoplanets with a habitable zone around G, K, or M stars. There's no mention of atmospheres. If you can find data on that, you're doing better than I am. I've scooped trying to find out the answer. How many of them have an atmosphere as well? And I think it's still early days determining, as I mentioned, the JW Space Telescope helps to determine if you've got an atmosphere. And of course, it's easier to analyse, first of all, some of these big gas giants and so on. So they're just starting to get that data together. Early days. And as for the signatures, these biosignatures, and that's formed by the light from the host star travelling towards us here, and some of it skims through the atmosphere of assuming it's got an atmosphere here, skims through it here, and the James Webb is able to detect that. Not only detect it's got an atmosphere, but it's able to analyse with its spectroscopy what sort of molecules are going on in the atmosphere from the light that's filtering through the atmosphere of an exoplanet. And let's have a look here. Like I said, next month's talk is going to be on spectroscopy, how astronomers learn about stars and exoplanets through the light that they see. So what sort of chemicals are we looking for? Oxygen and ozone, big indicator of life. Of course, oxygen can be formed without life. For example, ultraviolet splitting up of photodissociation of water in the atmosphere. But that's a big one. That gets your attention. Photosynthesis. Methane gas. Methane gas can be produced geologically or biologically, but certainly gets your attention. Incidentally, if you get two of those together, both of them can be made biologically or non-biological. Both of them degrade in the atmosphere. But if you see them, that's got your attention, but it's not a definitive thing. You see both oxygen and methane together, that's a real much stronger indication of life going on, because you've got two chemicals that can be produced either way, but definitely biological. Both get broken down and degrade. Both react with one another. So if there's still plenty of oxygen and methane going around, you've got life pumping it out there. You know, you've got some sort of very strong source pumping both gases out because both combine together. Water vapor, obviously, because you're looking for water. Water is the universal solvent for carbon-based life. Nitrous oxide, or laughing gas, that's produced only by microbes on Earth. So if you see that there, it's funny, but it's still, it's very strong. Organic sulfur compounds like dimethyl sulfide and dimethyl disulfide. That's recently been in the news with exoplanet K2-18b, that they think they've found that. We're going to talk a lot about that next month. I'll show you those findings are very, very tentative at the moment, but still interesting. Still gets your attention. They are only produced by microbes on Earth, as far as we know, with plankton and stuff. But throwing a cat in them with the pigeons, they found it, remember Comet 67P that they analysed, they found dimethyl sulfate on one of the comets. So that's raised a lot of questions. How are there other chemical reactions that can do it? Phosphine that they thought they found in the atmosphere of Venus a few years ago and then found, maybe not so. But that's biologically produced. So if you confirm phosphine in the atmosphere of a planet, that's another biosignature. And of course, if you see chlorofluorohydrocarbons, CFCs, you know you've got idiots on the planet. Don't go there. Put your cloak on and drive past. Okay, so here's some data here. This is off a hot gas giant, but I put this a little bit clearer for you to see from the James Webb. See water vapor, carbon monoxide, dioxide, some sulfur dioxide there. But you can see that's the sort of data they get. It's instead of dips, you actually see, because this is on this side here, on the y-axis, it's the amount of light that's been blocked. So you see peaks, not dips, that you might be otherwise used to. So that's the sort of data that they get. Like I said, we're going to be talking a lot more about that next month, about best fit models, how they work out what all that means, and how they match it up with molecules. This is the one that's in the news recently. Yeah, let's just go back. I know why I put that in there. So here's your nice big humps and stuff like that. This is the data from MIRID, the mid-infrared data on the dimethyl sulfide in K2-18b. Not big convincing, so the computer models, there's a lot of disputes there about what models they've used to actually try and fit that data to fit the models. So very tentative. But anyway, that just gives you a flavour of where they're heading with this. Is real early days yet, but where they're heading with it all. Of course, on the horizon, hopefully it should be up and running by 2028. This is the extremely large telescope. It's in Chile, Atacama Desert. This is going to hopefully blow everything out of the water to 40-metre size mirror that will be able to see into the near infrared because it's high up in a mountaintop above over 90% of the water vapour. Infrared telescopes ideally are up on a mountain or in space because water vapour absorbs infrared, so you want to get above the water vapour. So this is going to be high up above the water vapour, 40 metres diameter telescope. Whew. Wow. That's really going to blow all this out. So let's wrap up. It's getting on summary and the implications, what to expect. So what have we learnt so far? Planetary systems are common. We are not unique. Life arose on Earth early, but it was simple for over 3 billion years. All life on Earth is carbon-based because it's abundant and it forms strong bonds. I hope I've convinced you of that. Hence, detectable life from what we know on Earth, this is the best we can do, will most likely be simple, such as slime, simple cells, and carbon-based. So it makes sense. That's what we should be looking for. If we find something else, that's great, that's exciting, but that's a good place to start looking. The best environment for life is a rocky planet, obviously with an atmosphere to support water, to support life, and the habitable zone, that sweet spot where liquid water, it's not too hot, not too cold, and a stable, long-living star such as a G or a K spectral class. It's main sequence star. And spectral analysis of an exoplanet's atmosphere, such as the James Webb and hopefully extremely large telescope up and running in 3 years, may detect chemical signatures of life, such as oxygen, methane, nitrous oxide, and dimethyl sulfide. So, from our talk, origins, conditions, and signature of life, what should we be looking for? This is your message. If there's one thing you can store away to take home, life in the galaxy will be abundant and detectable, but most likely will be simple slime. Thank you. Any questions? If you haven't got a handout, there's actually a few more up here. You can grab one later on. Or if you want a PDF, you can just take a picture of that. That's the QR code to my file with it on at home. Any questions?